Hello guys, yesterday we studied about the moment of inertia of a uniform disk. Again, today I am explaining this moment of inertia of a uniform disk. Now, yesterday I completed fastly. Now I am giving some time for explaining this moment of inertia of a uniform disk. Now, before that, what is meant by the uniform disk? Now, this uniform disk, we can say this disk as the uniform disk when surface density is same throughout this body. When surface density is same throughout this body, then it is called as the uniform disk. Now, this uniform disk is the two-dimensional quantity, two-dimensional object. It is a two-dimensional object of negligible thickness. Now, mass per unit area, that is the surface density. Now, the sigma is equal to mass per unit area, that is the mass upon area. Mass upon area. When this mass per unit area of this body is same or constant throughout this body, it is called as the uniform disk. Now we want to obtain the relation or derive the relation for the moment of inertia of a uniform disk. Now in order to obtain the moment of inertia of uniform disk, now consider this is the uniform disk of mass m. Its mass is m, while we know area of this disk is A is equal to pi r square. A is equal to pi r square. Now r is the radius of this disk, while m is the mass of this uniform disk. Then area of this disk is A is equal to pi r square. Therefore, surface density sigma surface density of this uniform disk is m upon pi r square. It is equal to m upon pi r square. Now this is the surface density of this uniform disk, or this is the density of this material with which this uniform disk is made, and this sigma is equal to m upon pi r square. Now this figure shows the disk. Its mass is m, while area surface area of this disk is pi r square. Then this sigma is equal to m upon pi r square. Now it is a circular object. Now the disk is always in circular shape, therefore it is a circular object. Now consider it is divided into small elements. Now the small elements are rings. In other words, we can say that consider it consists the number of concentric rings. These are the circular rings. Suppose this is the disk. Now suppose this is the disk. We can divide the number of rings. Now we can divide this disk into the number of rings. Number of rings. Now consider it consists the number of rings. One such a ring. Now it is shown by the shaded region or shaded portion in this figure. Now this is the ring. Now it is considered as the small element of this uniform disk. Now consider dm is the mass of this small element or this shaded ring. This is the mass of this ring, and area from this we can find the area of this ring. Now this is the ring. Its thickness is dr. Its thickness is dr. Now this dr is very small. This dr is very small. Therefore, average radius of this ring is considered as the r. Average radius of this ring is considered as the r. Now entire mass of this ring is at distance r. At distance r from the axis of rotation. From the axis of rotation. From this we can find the moment of inertia of this ring. Now moment of inertia of this ring, we know moment of inertia of ring standard formula is m r square, in which m is the mass of the ring while r is the radius of this ring. Now in this case, capital M is mass while capital R is radius. But in this ring is at distance R, means it is at distance R from the axis of rotation, and this mass of this ring is small dm. Now width of this ring is dr. We are using this width for finding the area of this ring. Now from this we get the moment of inertia of this ring. It is equal to IR. It is equal to IR. Now radius of this ring is R. Instead of capital R, we are using this small r. Therefore, it is equal to R square into dm. Now this is the moment of inertia of this shaded ring. Actually, it is considered as a small element of this uniform disk. It is the small element of this uniform disk. Actually, this disk is divided into the number of concentric rings. Number of concentric rings, and we are taking one such ring. Its mass is dm. Now it is at distance r from the axis of rotation. Therefore, moment of inertia of this ring, it is equal to r square into dm. Now, when we are dividing or when we are considering the large number of concentric rings, their radii increases from 0 to r. Their radii increases from 0 to r. Yes, the ring which is outer ring, the ring which is outer ring, its radius is capital R, and inner ring which its radius starts from 0. Therefore, it consists the concentric rings of radii, and this radii increases from 0 to r, or this radii varies from 0 to r. Now, from this small element, we can find the moment of inertia of this total body. Now, total body is uniform disk. Therefore, we can say that by integrating this moment of inertia of small element, we can obtain the moment of inertia of total body or total object. Now, moment of inertia of uniform disk, it is represented by I, and it is equal to integration of this moment of inertia of small element. Now, it is equal to integration of r square into dm. Now, this is the moment of inertia of a uniform disk, but this radii of concentric ring varies from 0 to r. Therefore, these limits are taken as the 0 to r. Now, this is the moment of inertia of uniform disk. Now, we have to substitute the value of dm in this equation. Now, we know dm is the mass of this small element or mass of the ring. This is the mass of ring, and its width is dr. Now, when we cut this ring at any position and when we are stretching, then this circumference is converted into the length, or we can take this circumference as the length, while dr is the breadth. Now, in this case, we get this area of small element, area of ring, it is equal to A or dA, it is equal to 2 pi r. 2 pi r, it is the length of this ring or circumference of this ring, and its thickness is dr. Therefore, we get this area is equal to 2 pi r into dr. Now, dm is the mass. From this, we can find the sigma. That is the surface density of this ring. Now, surface density of this ring is same as that of the surface density of the disk, because it is made with the same material. Therefore, surface density is same. Now, this surface density, by using this, we get this as the mass upon area. Mass upon area is dm upon 2 pi r into dr. From this, we get this dm is equal to 2 pi r dr into sigma. 2 pi r dr into sigma. Now, by substituting this value in this equation, this I is equal to integration of integration of 0 to r. Now this is r square. Now value of dm is 2 pi r. Now this is r square, means it is placed as it is. Now dm is equal to 2 pi r dr into sigma. Now by multiplying with this r square and r, we get this value as r cube. Therefore we get this as the 2 pi 2 pi sigma 2 pi sigma into r cube dr. But 2 pi sigma is constant, but this 2 pi sigma is constant. Therefore we can take this constant out of integration sign, and it is equal to 2 pi sigma 2 pi sigma. Now integration of r cube dr, r cube dr. Now we know formula for the integration. There is a general formula for the integration. This general formula is integration of x raised to n dx. Integration of x raised to n dx. We get this as the x raised to n plus 1 upon n plus 1. It is equal to x raised to n plus 1 upon n plus 1. Now in this case, this is the r instead of x. Here we are observing this term as the r cube, and instead of here there is a 3, and by using this formula we can write the integration of r cube, and it is equal to, now this I is equal to 2 pi sigma 2 pi sigma. Now integration of r cube. Now suppose this is the r raised to n, then we get this as the r raised to n plus 1 upon n plus 1. But n is 3, therefore it is r raised to 3 plus 1, that is 4 upon 4. Now it is equal to, we get this as the r raised to 4 upon 4, and limits are 0 to r. Now when we are taking the integration, and if there are a limits, initially we are substituting the upper limit. We are substituting the upper limit, and after that we are substituting the lower limit, and we are taking the subtraction of this. Now it is equal to 2 pi sigma. Now by substituting the upper limit, we get this as the r raised to 4 upon 4 minus, instead of r we can substitute the 0. Now 0 raised to 4 is 0, therefore it is equal to 0. Therefore we get this as the 2 pi sigma into r raised to 4 upon 4. 2 pi sigma into r raised to 4 upon 4. But this sigma is equal to, this sigma is the moment of inertia of the sigma is the surface density of the uniform disk, and so this sigma is equal to m upon pi r square. This sigma is m upon pi r square. By substituting this value, this I is equal to, we get this as the 2 pi into m upon pi r square into r raised to 4 upon 4. Now by cancelling this pi, also r square, there is a r square only. Now 2 ones are 2, 2 twos are 4. From this we get this as the I is equal to 1 half into m into r square. Now 1 half m r square, and this is the moment of inertia of a uniform disk, that is the I is equal to 1 half m upon r square. Now this is thus we obtain the relation for the moment of inertia, and this moment of inertia of a uniform ring is 1 half m r square. Now yesterday we also found the moment of inertia of a uniform ring, that is only the mr square, while moment of inertia of a uniform disk is 1 half mr square. Now by using the same relations, or by using the same method, we can obtain the moment of inertia of different geometrical shapes. Now there are different geometrical shapes such as ring, ring, disc, also cylinder, sphere, all these are the geometrical shapes. In this case, hollow, also there is a hollow cylinder, hollow sphere. These are the geometrical shapes, and we can find the moment of inertia of different geometrical shapes experimentally in this way, and these moment of inertia are given in a table number 3. Few moment of inertia are given, means there are formulas which are given in a table number 3 in book. Actually, this table is on last page. You can observe the different moment of inertia for the different geometrical shapes. Now this is about the moment of inertia of a uniform disk. And now our next point is radius of gyration. In rotational motion, we already discussed about the moment of inertia, and this moment of inertia is also depends upon the radius of gyration. Now, what is the radius of gyration? Actually, this is also a physical quantity. This is also a physical quantity which gives the more information about the moment of inertia. Or this is the factor which gives the distribution of mass from the axis of rotation. Now, generally we know mathematical or theoretical calculation of moment of inertia. Theoretical calculation of moment of inertia is possible only for the bodies or objects. It is applicable only for the objects for the mathematically integrable geometrical shapes. Means we can find the moment of inertia of only these bodies which are in a geometrical shapes, and in this case we can find the theoretical moment of inertia. Theoretically we can calculate the moment of inertia in case of the bodies which are mathematically integrable geometrical shapes, but experimentally we can find the or we can determine the moment of inertia of any object, or in other words we can say that experimentally we can find the moment of inertia of all bodies, but mathematical calculation or theoretical calculation we can do in case of some bodies. These are the integrable geometrical shapes. But experimentally, we can identify or determine the moment of inertia of all bodies or any bodies. And this moment of inertia, we know this moment of inertia is mr square. This moment of inertia is depends upon the mass, and it also depends upon the how mass is distributed about the axis of rotation, or how this mass is distributed about the axis of rotation, or how this mass is distributed around the axis of rotation. Suppose one body is rotating about this axis. One body is rotating about this axis. Now this moment of inertia depends upon the mass of this body which is revolving. And it also depends upon the how this mass is distributed about the axis of rotation, or how this mass is distributed around the axis of rotation. Now, if we are interested, or if we are interested to knowing only the distribution of mass, only the distribution of mass about the axis of rotation, in this case, we can write the moment of inertia. This moment of inertia as the it is equal to mk square. Actually, this equation shows that m is the mass of the object, while k shows the k is the distance of this object from the axis of rotation. Actually, this equation shows that mass is effectively at distance k. Mass is effectively, or mass is effective at distance k, and this k is called as the radius of gyration. This k is called as the radius of gyration. In other words, we can say that if k is the radius of gyration, then moment of inertia of body is I is equal to mk square. I is equal to mk square. Also, it shows the relation that as k is larger, when k is larger, then we can say that mass is away from the axis of rotation, or mass is farther. For larger value of k, mass is farther from the axis of rotation, and this is about the radius of gyration. Now listen again, this radius of gyration, how we can explain the radius of gyration. Now theoretical calculation of moment of inertia. Theoretical calculation of moment of inertia is possible only for the mathematically integrable geometrical shapes. Means, in other words, we can say that theoretical calculation we can find by using the theoretical calculation we can find the moment of inertia of a body which are in geometrical shape. But however, we can find experimentally the moment of inertia of any object. Yes, we can find the moment of inertia of any object experimentally. And when we are finding experimentally, it is found that this moment of inertia depends upon the mass of the body or mass of the object. It also depends upon the how mass is distributed about the axis of rotation, or how mass is distributed around the axis of rotation. Now, if we are concentrating, or if we are interested to knowing only the distribution of mass of the object about the axis of rotation. In this case, we can represent the moment of inertia as I is equal to mk square. Now, in this, m is the mass of the body, while k is the radius of gyration. Actually, this k indicates, or it shows the mass is effective at k. Mass is effective at k, or mass is effectively at distance k, and this k is called as the radius of gyration. This k is called as the radius of gyration. In other words, we can say that if k is the radius of gyration of the object about the axis of rotation, then moment of inertia of this body is I is equal to mk square. Also, additional knowledge is given that for larger k, this mass is distributed farther, or mass is distributed away from the axis of rotation. Now, this is about the radius of gyration. Now, next point is theorem of parallel axis and perpendicular axis. Now, first of all, we want to discuss about the theorem of parallel axis. Now, what is the theorem of parallel axis? Now, theorem of parallel axis. We want to obtain the formula how we can find the moment of inertia about any axis of the object. When we are finding the moment of inertia of any object about the axis, sometimes we are using the different methods. Suppose this is the body and this is the axis passing through its center. Now this is the moment of inertia about this axis. But if we want to find the moment of inertia about this axis, then in this case we are tracing the or we are taking the parallel axis. We are taking the parallel axis and we are transforming this information in the related with the parallel axis, and we are finding the moment of inertia of this body about this axis. Suppose if we want to find the moment of inertia of this body about this axis, at that time we are taking the axis perpendicular to this axis. This axis is perpendicular while this axis is parallel to this axis. And by taking this perpendicular axis and parallel axis, we are finding the moment of inertia of this geometrical shape. Moment of inertia of this geometrical shape. And these laws are known as the, or this method is known as the theorem of parallel axis and theorem of perpendicular axis. Means we are taking sometimes the parallel axis and sometimes we are taking the perpendicular axis, and from that we are finding the moment of inertia of this body or this object, and these laws are stated as the theorem of parallel axis and theorem of perpendicular axis. Now what is the theorem of parallel axis? Actually in this case there are two axes. These two axes are parallel. Now for parallel, when we are applying the parallel axis by using the parallel axis theorem, by using the theorem of parallel axis, we can find the moment of inertia of any body or any object. It's either this is laminar or not laminar. Then also we can use the theorem of parallel axis. Now, in order to apply the parallel axis theorem or theorem of parallel axis, we need two parallel axes, or we need the two axes parallel. We need the two parallel axes. From that, one axis is passing through the center of mass of the body or center of mass of the object. Now, in this case, we are by using this two parallel axes, we are finding the moment of inertia of this body about given axis. Suppose this is the axis, we want to find the moment of inertia about this axis. But for that, you have to take the two parallel axes. Another axis should be passed through the center of mass of the body. Then we can apply the theorem of parallel axis. Now, in order to apply the theorem of parallel axis, we need two axes parallel to each other. One of them is passing through the center of mass of the body. Now, this figure shows the object. Suppose this mass of this object is m. Mass of object is m. Now it consists the two axes. First axis is MOP. Now MOP is the axis passing through point O, and moment of inertia about this axis is represented by IO. IO means moment of inertia of the axis. This axis is passing through the point O, therefore it is represented by IO. Another axis is ACB. Now another axis is ACB. It is the axis parallel to the given axis. It is the axis parallel to the given axis and passing through the point C. Passing through the point C, and moment of inertia about this axis is represented by IC. Now, actually this another axis ACB is at distance h. ECB is at distance h from the given axis, and now we want to find the moment of inertia about this axis, moment of inertia of this object or body about this axis. For that, consider the mass element is placed at point D. Mass element means this is the small element of this body. Small element of this body. Actually, it is divided into the large number of small elements, and we are considering one small element. Small element. It is known as the mass element. Its mass is dm. It is located. It is located at point D. It is located at point D. Now, this small element is at distance OD from this axis, and it is at distance CD from the axis ACB. Now, they actually these are drawn by the dotted line. Now, this OC is produced. Now, this OC is produced, and DN is drawn perpendicular. DN is drawn perpendicular on OC produce. Actually, this we can extend this OC. It is known. It is called as the OC produce in this direction. And this DN is drawn perpendicular on this OC. Now, this OC DN is perpendicular. Then we get this as the ODN is the right angle triangle. Now, this ODN is the right angle triangle. From this, we can write this moment of inertia IC. Moment of inertia of this object about the axis passing through the center of mass of body. It is equal to, we know moment of inertia formula, we know this moment of inertia is integration of r square into dl, in which r is the distance of object, or small element, distance of small element from the axis of rotation. Now, in this case, this CD from this axis, actually CD is the perpendicular distance of from the axis of rotation. Now, small element is at D. Now, this is the perpendicular distance from the axis of rotation. Actually, these are perpendicular to the plane of body. Then this distance is CD is also perpendicular to this axis of rotation. Now, from this we get this as the integration of, instead of R we are using this distance. This distance is DC or CD. Now, it is equal to DC square into dm. This is the moment of inertia about this axis. And so, moment of inertia about this axis, moment of inertia about the axis MOP, it is represented by IO, because this axis is passing through point O. Therefore, it is represented by IO. Now, this moment of inertia, again, this small element is at distance DO. From this axis of rotation. Therefore, we can write this as the dO square into dm. Now, this is the moment of inertia of this object about this axis, and now we want to derive the formula for this moment of inertia. Now, DO, this is the right angle triangle. Now, DNO is the right angle triangle. For this DO, we can apply the Pythagoras theorem, that is dn square plus NO square. It is equal to, we can write this as the dn square, it is equal to dn square plus NO square into dm. dn square plus NO square into dm. But NO, we can write this as the NC plus CO. NC plus CO or OC. We can write this as the integration of dn square plus NO. NO is the NC plus CO. NC plus CO bracket square into dm. Now, this dn square remains as it is. Now, integration of dn square plus. Now, this is same as that of the that of the equation a plus b bracket square. A plus b bracket square, we can write the expansion as a square plus twice nc dot co plus co square. Therefore, we get this as the nc square. Nc square plus twice nc dot co plus co square into dm, co square into dm. Now this co is equal to, actually this axis is at distance h from this axis. Therefore this co or oc, it is equal to h by also this dn square plus nc square. This dn square plus nc square, it is again by using in small right angle triangle Pythagoras theorem, this CD square or DC square is equal to dn square plus nc square. Therefore, nc square plus dn square plus nc square is replaced by the dc square. Therefore, we get this as the dc square plus twice nc co plus co square into dm. Now this CO is equal to h. By substituting this value, we get this as the integration of dc square plus twice nc into h, twice nc into h, and plus h square into dm, h square into dm. Now this CO is equal to h. By substituting this value, we get this as the dc square plus twice nc dot h plus h square into dm. Now by separating the integration, we can write this as the integration of dc square dm, integration of dc square. Yeah, we can write, actually we can take the we can take the brackets here also. Now this dc square dm plus integration of twice nc into h dm, twice nc into h dm plus integration of h square dm, plus integration of h square dm. But this h is distance and it is constant. We can take this h out of this integration side. We get this as the IO is equal to, this IO is equal to integration of dc square dm plus h into integration of twice h, we can write this as a twice h into nc sorry, we can write this as a twice 2, we can write this as a 2 into nc into h, or sorry, we can write this as a twice h into integration of nc dot dm also plus h plus h square into integration of dm. Now this is the formula, actually for the this is the modified formula up to this. This is the integration of dc square dm plus twice h into nc dot dm plus h square into dm. But this integration of dc square dm, it is equal to dc square dm, it is equal to ic. Therefore, this IO is equal to ic plus, now twice h into NCDM. Actually this NC is the distance of the point from the center of mass. Distance of the point from the center of mass, and mass distribution is symmetric. Mass distribution of the object is symmetric about the center of mass by definition. By definition of the center of mass, this integration of nc dot dm, it is equal to 0. Integration of nc dot dm. Actually, this dm represents the mass, but this nc shows the distance of the point from the center of mass, but this mass is symmetrically distributed about the center of mass. Therefore, this moment of this mass, moment is actually, this is the moment of mass. Moment of mass at the center of mass is always zero. Therefore, this quantity is zero. Also, this x square. Now integration of dm. Now dm is the mass of small element. It consists the large number of small elements. Now integration of this small element. Suppose it consists the large number of small elements. Now dm1, dm2, dm3, dm4, all these are the masses of this small element. If we take this summation or integration, summation of all these masses, it gives the total mass of this body. Means integration of dm, that is equal to the total mass of the body, and we already considered m is the mass of this object. It means that this integration of dm, it is equal to capital M. Now, by substituting this, we get this as the s square into m. Therefore, IO is equal to IC plus mh square. IO is equal to IC plus mh square, and this is the mathematical expression for the parallel access theorem, or this is the mathematical form of the theorem of parallel access. Now listen, this moment of inertia theorem of parallel access. Now in order to apply the theorem of parallel access, we need two axes parallel to each other. From that, one is passing through the center of mass. Now this figure shows the object of mass m. Figure shows the object of mass m. Now ACB is the, MOP is the axis passing through point O, and another axis of rotation is ACB. It is parallel axis to the given axis. It is parallel to the given axis, and it is at distance h from the given axis. Now we want to find the moment of inertia about this axis. Now consider small element of mass, or mass element is D, is situated at point. It is placed at point D. Mass element is situated or placed at point D. Now, when OC is produced, this DN is drawn perpendicular. Then, moment of inertia about this axis is IC is equal to DC square, DC square dm, while IO, moment of inertia about this axis is IO is equal to DO square plus DO square into dm. Now, DO is the distance from the axis of rotation. Now, by using this formula, we can write these two formulas. But this DO, by using the Pythagoras theorem, the DO square is equal to DN square plus NO square. But this NO is NC plus CO. By using this expression, we get this as the DC square, actually we get this as the dn square. By expanding this bracket, we get this as the nc square plus twice nc dot co plus co square. Now this nc dn square plus nc square, again by taking the small right angle triangle, this dc square is equal to dn square plus nc square. We get this as the dc square plus twice nc dot co plus co square. Now from this, actually when we are substituting the values, actually it gives this CO is equal to H, but this product, integration of product of this NC into DM is 0, because this mass is distributed symmetrically about the center of mass. This NC represents the NC represents the distance of object or distance of point, but this mass is symmetrically distributed about the center of mass. By definition of center of mass, this integration of SK dot CM is equal to 0, and integration of DM, Integration of dm means it is the sum of all the masses, and that is equal to total mass of the body, and it is equal to m. By substituting this value, we get this as the IO is equal to IC plus mh square, and this is the mathematical form of the theorem of parallel axis. And next part we will discuss in the next lecture.